Okay, so welcome back. Hopefully you're watching this video having watched the first video just about opening Grasshopper and making sure the appropriate Python packages are included when you do that. So in this video, what I'm going to do is I'm going to go through the beam example. So the PDF of the canvas is also available to help you with this. So it's really that structure that I'm following for the Grasshopper definition, but I just thought I would outline the problem that we're going to be looking at first of all, and obviously once we look at this specific example, we can actually go on to do lots of things very rapidly. So change the beam type. So for example, change it from a cantilever to a simply supported or a fixed ended, or change the loading and so on. But we'll start with this simple example because it will allow us just to verify the values that we're getting out from the analyses at the end. So the example is just going to be a simple cantilever like so. So a fixed end here, just a point load acting down at the free end here. We've got a total length L, and I've labeled the point load P as well. And what we're interested in, so obviously we're going to get results out in the global axis system. And I've indicated that at the free end here, that means that we have a downward deflection of minus PL cubed over 3EI. And actually we have a clockwise rotation. So in our global axis system, that means that we have a negative rotation of PL squared over 2EI. So we can just check those values later on, and I'd encourage you to do that once we've completed the Grasshopper definition. The other information just to draw attention to, so obviously if we have the P as the applied loading, then we'll have a vertical reaction going up the way of P here, and we'll also have a moment reaction of PL acting anti-clockwise at the support there. So those are the forces that we expect to find when we go back through and solve for the force matrix F at the end. The other thing just to mention is obviously the other output that we want is we want the beam end forces, and we want them in the cross-section axis system, which I've shown here. And the reason for that is we want to be able to go on to plot the axial force, the shear force, and the bending moment diagrams. So here I've just indicated the positive conventions for those. If you take a cut and then you're looking to the left of that cut in the cross section of the beam, I have included the axial force, although obviously that's not going to be relevant for this loading scenario. But then I've included the shear force diagram here. So we have a negative shear force, remembering that it's the internal force at the cut required for equilibrium. And then in terms of the bending moment diagram, we actually have a positive bending moment, PL. So that's at the support, but this is the internal bending moment. And then that will linearly decrease. So basically the integration of the shear force diagram plus obviously the initial bending moment, but that will linearly decrease until we get to 0 at the free end here. The final thing just to mention about bending moment diagrams, so although obviously there are different conventions out there, generally I will always treat tension or the tension side as positive, so the bending moment diagram will appear on the side of the beam under tension. So in this case, obviously what we're saying is that the top of the beam is under tension. So having just outlined the problem, what we'll do is I'll just pause and then we'll come back with a Grasshopper canvas open. Okay, so I've got my Grasshopper canvas open. I've also actually got the Rhino canvas beside it. And something that a few of you might remember from first year is it's useful to be able to visualize what you're doing. but it can quickly get a bit kind of cluttered if you're looking in the Rhino canvas at everything. And so it's normal to click here, and what that should do is it'll only preview the geometry for selected objects that we're interested in. The other thing just to highlight, so I have already given my file a name, but what I want to remind you is that the autosave for Grasshopper is a little bit prone to issues. So do regularly save your work, and obviously initially you might go to File, Save, or Save Document As, and then very regularly I would be saving the document from there. So the first component that I'll put on is the bifocals component. So that's really just going to help guide us through as we do this video, because it's just going to add component names as we go through. The next thing that I want to do is, obviously for a beam, I want to just construct a line, and the simplest way of doing that while keeping everything defined in Grasshopper is I'm going to construct 2 points, and then I'll join a line between those 2 points. And that will also allow me to quite easily control the length or even the angle of that line. For the beam example, obviously the angle compared to horizontal is just 0. So I'm going to define the points by changing the x coordinate for those. So to get a point, we actually want to construct the point. So it's construct that we're initially typing. So that gives us the point there. And we can see if we hover over the X, the Y, or the Z inputs, that actually these have default values of 0. So basically, if we do nothing, it will give us the origin. And that's what we're going to do just now. So if I've got a component, I can just copy and paste it. So if I do Control C here, and then Control V down there, that's just given me my other point. And then what I'm going to do is I'm going to use a panel, so like so. Generally, if you're using panels, you immediately want to change them to multi-line data. Basically, that just makes the data a little bit easier to handle as we go through. So that component, the construct point component, is just showing up red because at the moment, obviously, it doesn't have any useful input to it. But I'm going to make my beam 1 meter long. So obviously, if I'm putting in the length units in millimeters, I'm making my beam 1,000 millimeters long here. So that's the 2 points. And then the line, very straightforwardly, again, we just need to make sure we don't select the wrong component. So this line component is just a storage for a line type. This is the line component that we actually want. And we can just connect our 2 coordinates into that. If we just briefly go over to the Rhino canvas, then you can see if I zoom out, there we have the line that we're interested in there. So the final thing that I want to do is just sort of good management of my Grasshopper canvas. So just middle button click on the mouse. I'm going to group it. So grouping is a very easy way to basically keep track of things. Then I'm just going to go into the group, right click, and I'm going to give it a name. So in this case, I'm just going to say build a beam is what that group's doing. And we can see quite quickly that some of the labeling is getting in the way slightly. So I'm just going to briefly turn off the bifocals just to show you the effect of doing that. And actually the canvas PDF that you have is done without bifocals on, just to make things a little bit easier. Okay, so we've got our beam basically. The next step is we're going to want to divide that down into a number of elements. just so that we can begin to see the effect of altering the number of elements. So I'm just going to pause here for a second, and then I'll be back to do that part. Okay, so I'm going to introduce something that doesn't necessarily need to be done for the line element, but is useful if you have a polyline or any other form of curve where the domain might not immediately map onto a domain between 0 and 1. And the reason for this is because we're going to use a shatter component command basically to produce individual line segments for our elements out of the initial line that we have here. So the component that I need is something called curve domain. So hopefully that will come up. So curve domain there. And then the other thing that I'm going to do is I want to have a domain. So actually I want to construct a domain. And I'm going to leave these as the default values between 0 and 1. So obviously my line is the curve in this case. And all that's doing is it's mapping whatever curve I put on onto a domain that will run between 0 and 1. So the next component that I'm going to add is the shatter component. So as I mentioned, what this does is it takes input as, in this case, values between 0 and 1, and it will then shatter whatever curve we put in into a number of segments from that. So obviously I'm going to feed my curve in here, and I want to be able to shatter so that I end up with however many elements I want. Each of them basically should be the same length. So the way we're going to do that is, first of all, we're going to have a panel. So remembering to make that multi-line data straight away. And this panel is basically the number of elements that I want to use. So I'm going to set 8 initially. And obviously this is something that I'd encourage you to play around with just to see the effect of the results, you know, of altering that value. And you can easily take it up to a few hundred and everything will still run fine at that. So the next thing that I'm going to do is I want an x to the minus 1. Or actually, sorry, it should be x to the power minus 1, I think. Okay, we'll just find what it is. Okay, so what we needed to do to get the component I wanted, it's just 1 over x, so effectively x to the power minus 1. So I'm just going to join that up there. So if we have 8 here, we can see here, that just gives us 1 divided by 8, basically. So the next component that I want is a series component. And I'll just briefly change bifocals back to on so you can see what's going on. So the inputs to the series component, we have a start number, and I want to just leave that as 0. We have the number, so the step size rather. So that was why I did the 1 divided by 8 in this instance. And then we have a count, so that's the total number of steps that we want to go. So we can just join the 8 up to our count. We can have this through as our step size. So that would give us an output of 0 through to the 0.875. Because I don't actually want to shatter right at the beginning of the line, what I'm also going to do is just connect that up to the start. So now we have shatter points between 0.125 and 1 regularly spaced. So we can then use that as the input to this one here. So as the t, so as the curve parameter basically, and that gives us 8 elements. These are going to be, but 8 shattered lines from that original line. And then what I'm going to do, just to allow me to visualize that information, so I'm going to put the line here, just a sort of holder basically, and I'm going to connect it up, and I'm just going to have a quick look at the structure here. So again, this is not necessarily something you need to do when you're doing a simple beam example like this, but it would be common then just to flatten that information. So that's going to then just put all of the lines, so basically all of the elements that we might want to use, it just puts them in a list, and it doesn't leave them in any sort of tree structure. So the final thing for this section here, again, I'm just going to group my elements, and I'm going to give this group just the name dividing each edge. So again, although here I've just got one beam, so one edge, obviously structures could have lots of edges, and I'm just going to say into and the number symbol, and obviously here 8 is the number in this instance, but that then completes the next stage of our build. So I'll just pause there, and then we'll continue on in a second. Okay, so the next thing that I want to do is for each line or each element, I need to define the start and the end points, and they're obviously going to be my nodes. And then the final stage in sort of putting everything together for the mesh initially is I need to generate a unique set of elements and a unique set of nodes, and I just need to make sure that there's some consistent numbering on all of them. So to start that process, we can just type endpoints. So that gives me the start and the end point for each line, like so. Just tidy things up a little bit. And what I'm going to do is, this is a little bit of a cheat. So from the sets, I could actually construct a complete set, but I happen to know that if I take a set union, that will actually return a set of unique values anyway. So it's just a sort of very slight shortcut. So I'm just going to connect my start and my end nodes in there. And obviously there are 8 start nodes and 8 end nodes. But what this is telling me is that we have 9 unique points. So those are the ones that we're going to be interested in. The next thing that I'm going to do is I'm going to use something called a point cloud. So this is quite a quick way, basically. If you have a lot of points, this is going to enable us to search for an individual point within the point cloud and identify it by an indice very quickly compared to other techniques that you might see, particularly sort of using a closest point component or something like that. So this is the way we actually define a point cloud. We look at the point cloud attributes, and I'm just running the points that I've generated into this is the location input, and that allows me to generate the point cloud. And then the next thing that I'm going to do is look for closest points. But I need the component which is point cloud closest point. So I'm going to run my start points into one of those, and then I've got my point cloud has been generated here, so I can run that in there. And then I need another one of these, so I'll just do Control C, and then obviously Control V down here. And now obviously I need to make sure that the end point is the one connected in there. So I'm just going to slightly change the layout here, just for my own convenience really. And then that you'll see in the indice here, so that has defined the index that each of the points is at within the point cloud. So again, for a beam, this is very straightforward, but for a more complicated structure, this is obviously potentially a bit more difficult. So again, I'm going to group these, so middle mouse click to group them, and then I'm just going to say finding the start and end node of each element is basically what we've been doing there. Okay, so we're almost done in terms of defining the mesh. Obviously, we've got a little bit more to go afterwards, but the final step is going to just be to show that we can generate a set of unique nodes and a unique set of elements that we're going to visualize in Rhino, just to check in a second. Okay, so to do that, I want to just put all of the unique points. I'm going to put them into a point collection. So this was where we got the unique points from, and I'll just bring that down there. And then also, obviously, I want my unique set of lines. So they came from up here, so like so. And then the next thing that we'll do is just point number. So we'll just find that component. So we'll just find that. Okay, give me 1 second. Okay, so I know that the component that I want is actually up on display here, and it's this one. So it was point list was what I was looking for. So here I can just plug my points into the point list. What I'm going to do for the elements is I'm just going to find the midpoint or the curve middle for each of them, and then that will basically allow me to label each element as well. So again, we've got the point list for them, so like so. And although this has come up quite nicely here, so if I go back to the point list for the nodes, we can see we've got 0, 1, 2, 3, 4, 5, 6, 7, 8. And similarly, so remembering obviously that we start at 0 in Grasshopper. And if I go to the point list for the elements, so just to label the elements, obviously here then we have 0, 1, 2, 3, 4, 5, 6, 7. So 8 elements and 9 nodes in total. What we can just do is, because sometimes it can be a little bit tricky to get the size correct for these, we can add in a number slider, and that will allow us to adjust the size of that point labeling. Okay, so we might actually just increase the range on this. So I'll allow it to go all the way between 0.1, and then actually I'll take it to 100. So let's just see how that comes up. Okay, so that then you can see allows us to easily tune the size of the points that are appearing, and I'll just do the same down here. So the putting a number in and then just 2 dots between it and then the 100. And the reason I'm doing 100.0 is that then just gives me the level of accuracy basically that the number slider will operate over. So again, I'm going to do that for the element numbers. So just feeding that in there. And again, we can just make those a little bit bigger to see them. And obviously we can select the lines, for example, so we can see that those numbers are just appearing at the center of each element. If we go up here and select the nodes, so we can see they are appearing as we expected at the start and the end of each element. And then finally, I can add in the node numbers just there as well. So, final bit, just tidying up. So we'll call this group showing node numbers in Rhino, because obviously Rhino we're just using to preview everything. And similarly, I'll just select this, middle click, and then I'll call this showing element numbers in Rhino. Okay, so now that we've got to this stage, we've basically got quite a generalized way of producing meshes. There is a little bit more depending on the mesh type that you are producing, but hopefully that's something that you'll be able to explore in the coursework. I'll finish this video now, and then the next video is really going to be talking about how we go from this mesh information and how we start to get information into the Python component. So we'll bring the Python script in and we'll start thinking about how we have to define the input to get into that.